standing walking balance to look at gait patterns in cerebral palsy and some other applications.
Hi, I'm Maarten, also from KU Leuven. My research is about how aging affects balance control during walking and standing. I'm using OpenSim both for inverse analysis of my motion capture data and to predict how muscle weakness, for example, affects balance control.
Hi everyone, I'm Mohammed from Rice University. I work with BJ Fregley. So I use OpenSim to model the musculoskeletal system, of course, for a different type of patients. So we use the concept of muscle synergy to reduce the dimension of control and essentially do the control for multiple, populations, including stroke and cancer population with, osteosarcoma issue.
Hey, I'm Antoine from KU Leuven, so I work with Maarten and Friedel. So I do very similar kind of research. I mainly use OpenSim for now for predictive simulations of walking, so I try to understand what's the underlying motor control model, so what are you trying to do when we walk, and I also use OpenSim for simulations of walking in children with cerebral palsy.
Yeah, okay, thank you. So this group of people will be roaming around. If you have any questions at any time, you can raise your hand, they'll come and help you. Quick question, how many people have used OpenSim before, just to see? Okay, good, so some returning users, but a lot of new people here, that's great. So before we get into the hands-on portion, I'm going to give an overview of OpenSim. OpenSim is used by researchers around the world to study a wide range of movements. So some examples are, we've used OpenSim to study sprinting and what limits the maximum speed in sprinting, to study cutting maneuvers, to study complex upper extremity devices with parallel mechanisms, to optimize standing long jump distance, to predict how people walk on inclines, to study gait disorders like crouch gait for children with cerebral palsy, as you just heard about, to study eye movements, so this is one of the more creepy studies used in OpenSim, exercise equipment for the International Space Station to counteract muscle atrophy, and drop landings on uneven surfaces. So this is just a snippet of the research that is done with OpenSim, and you can see the movements that we study are diverse, but also the types of studies that we can perform with OpenSim are diverse. So some of these studies are inverse studies because we have experimental data that we're tracking and we're using that to estimate unmeasured quantities. Some of these studies are also forward or predictive, in which we're predicting a movement without tracking any data. So what are the elements of each of these simulations? This diagram shows how we think of OpenSim. In human and animal movement, our skeleton is driven by our muscles, and those muscles are coordinated by our nervous system. And OpenSim allows you to model each of these aspects using existing components or your own custom components that you bring to OpenSim. So the muscles. Most OpenSim muscle models are hill-type models. These models model the delay between neural excitation and when our muscles actually generate force. That's what we call activation dynamics. The muscles in our bodies attach to our bones via tendons that have some compliance and can store energy, and we capture that compliance and we model those tendons. And those tendons are described by this force-length relationship for the tendons here. The force that a muscle can generate also depends on the length and velocity of muscle. So this shows the force a muscle can generate as a function of its length, and so muscles can generate most force at an intermediate length, and the force you can generate decreases as shortening rate increases. The muscle curves are based on experimental data from muscle fiber experiments, and throughout the OpenSim community you'll always see a strong effort to build models upon experimental data and to validate those models. So the muscles generate a force along a path, and to convert those forces into joint moments, we model the path of a muscle. And so the path of a muscle is shaped by wrapping surfaces shown in teal here, and those wrapping surfaces represent bony geometry or other biological structures. For modeling the skeleton, OpenSim includes a variety of standard joints like slider, pin, and ball joints, but also provides the ability to use joint types that are useful for biological joints, which are often pretty complex. So this first video on the left shows a knee joint that's 1 degree of freedom, but we describe the translation of the shank with respect to the tibia using splines that are a function of the a knee flexion coordinate. The video on the right shows an ellipsoid joint that describes the movement of the scapula, the shoulder blade, on the surface of the thorax without any kinematic constraints. So that's a joint. OpenSim can also model contact between the foot and the ground or within a joint, say like in your knee joint, using compliant contact geometry. So this video shows a study on different strategies to avoid an ankle injury during a drop landing, looking at if our muscle reflexes are fast enough to prevent ankle inversion injuries. Others in the community have also used these compliant contact models to look at contact loads in the knee joint to discover walking patterns that can reduce knee joint load, which is important for those with knee osteoarthritis. So now the last component I'll talk about is the nervous system. You can model the nervous system in OpenSim using optimization criteria like minimizing effort or metabolic cost, or using feedback controllers to model neural reflexes, or anything in between. These neural models have been used to study the effect of exaggerated tendon stretch reflexes, or spasticity. So in this video on the top, you'll see a motion of somebody who has an intact nervous system, or a healthy individual, and on the bottom, someone with spasticity. And you'll see that with spasticity, the subject isn't able to extend their knee quite as much. So that's a glimpse of each of these components in OpenSim. Muscles generate force depending on their length and velocity. Skeletal geometry, we allow modeling complex biological joints. We can model contact between the foot and the ground or within a joint. And we allow complex neural controllers. And by combining these elements in different ways, we can study diverse animals, including humans, dinosaurs, and mice, and diverse movements. To perform multibody dynamics calculations, OpenSim uses the Symbology Library, which was developed by Michael Sherman, who, I don't know if maybe some of you are familiar, he developed the STFast library for multibody dynamics, and he now works at Toyota Research Institute on Drake. Symbody was developed with accuracy and speed in mind. Symbody performs forward dynamics calculations using an order n Featherstone-like algorithm, which allows us to simulate Atlas in real time. You'll hear more. Well, okay, so Symbody also gives you access to multibody quantities like the mass matrix, which allows you to implement model-based controllers like task-based controllers, which is what you saw in the Atlas video. This is a video of the Strawn-Beast walking mechanism, which each leg has 12 segments but only 1 degree of freedom, so it's a highly constrained system. One feature of Symbody that's important for biomechanics studies is the ability to perform what we call mixed dynamic studies, where some degrees of freedom are determined by forward integration or forward dynamics, while others are determined from experimental data. So you can prescribe certain degrees of freedom, and that's often useful for biomechanics. When you use OpenSim for your research, you don't start from scratch. OpenSim provides a standard format for exchanging musculoskeletal models, which has allowed us to form a repository of models created by the community. And that helps people reproduce and extend each other's research. So online, you can find lower extremity, upper extremity models, models of the wrist, the neck, or the spine. OpenSim can be used in a variety of ways, allowing diverse workflows. We have a graphical user interface that allows you to visualize a model and to use the standard OpenSim tools. The standard OpenSim workflow is that you have motion capture data, you scale a generic musculoskeletal model to your subject data, you perform inverse kinematics to obtain joint angles, and then you estimate muscle activity using an algorithm we call computed muscle control. But that's not the only thing you can do with OpenSim. If you want to build your own custom methods, you can use our Matlab or Python interfaces. And so in these interfaces, you can access the equations of motion for your model, or compute quantities like joint reaction forces, or really anything you might want from your musculoskeletal model. And many people have built trajectory optimization methods on top of OpenSim using these interfaces. One example, so you heard some examples of that from the people helping today. I'll highlight one exciting example from last year. some people in our lab, including Carmichael, used the Python interface in a machine learning competition at NIPS, a machine learning conference. So this shows some videos of people using reinforcement algorithms to train an OpenSim model to run as fast as possible. We also have a C++ interface, and that's used if you want to create custom model components, so your own muscle model. You can do that in Matlab, but you can also do that in C++. If you want to design your own neural controller, that's often done in C++. So these three interfaces we refer to our application programming interface because you can build your own applications using these interfaces. And you might hear us use that term API throughout the talk. Today we'll be using the Matlab interface to write our own scripts to build a model, and you'll also see a Matlab application that that Nick created in Matlab using the OpenSim API. Quick poll, how many people, I want to get a sense of how many people use Matlab versus Python. So if you use Matlab, could you raise your hands? Okay. And Python? Okay, cool. As for operating systems, we support Windows, Mac, and Linux. The Mac support is actually something new that's going to be in our upcoming release. We've only supported Windows for a long time. We support Linux, but we don't typically have pre-built binaries for Linux. But we often use OpenSim on Linux for running our trajectory optimizations. The OpenSim user base is growing and diversifying. The graph in the lower left shows publications using OpenSim broken up by different fields. So one thing you can note here is robotics. And this brings us to the topic of today's workshop, which is human-robot interaction. So how does an assistive device interact with musculoskeletal model? This is one of the most exciting areas for OpenSim, and one that we think is of particular interest to people at Dynamic Walking. We believe that the design of wearable robots must involve an understanding of the underlying biology. Dom Ferris and Greg Sawicki tested a passive exoskeleton a few years ago and found that even though their device reduced muscle force, the device did not significantly reduce metabolic cost. So to understand why, they used OpenSim to simulate their experimental results, and they found that some muscles, in this case here the medial gastrocnemius, operated at shorter lengths with the exoskeleton, which resulted in a reduced ability to generate force. So I showed this plot earlier. This is the force length behavior of a muscle. So we can use OpenSim to estimate quantities that we could not observe, or that we chose not to observe in an experiment. So that's an inverse study. We can also use OpenSim to make predictions. So 2 years ago, Tom Uchida from our group used OpenSim to design devices to reduce the metabolic cost of running. He found that the optimal device torque profile usually does not match the net joint moments generated by muscles. Then Greek Lee and his colleagues from Connor Walsh's group applied these findings to see if they can improve the design of an actual device, which assisted hip extension. And so this bar graph shows the results. The important comparison is between blue and red. Trying a torque profile based on the simulations, they obtained a greater reduction in metabolic cost than scaling down the biological net joint moment. So the simulation results were able to help improve the performance of an assistive device, which can help avoid expensive human experiments. And so we think there's a big opportunity here for biomechanics using simulation to design assistive devices for running, walking, or pathological gait. And so we'll give you just a small glimpse of how you might be able to do that, how you might be able to simulate an assistive device in OpenSim. So the goals for today, we want you to know how to build an OpenSim model from scratch. We want you to know how to interact with that model in MATLAB and plot quantities from your simulations. And then we want you to compete with each other to maximize jump height of a model. Okay, so for the first goal, we'll build a simple leg model with one muscle, and you're going to understand every component in this model. Then we're just going to hand you a more complex model with an assistive device, and we'll walk through that model, and then we'll use that model in a competition. So at this point, we can pause for questions. Does anybody have any questions? All right, great. Oh. Okay, so the model we'll build from scratch is a single leg, just one muscle, and we'll use it to simulate a knee-jerk reflex. And as I mentioned earlier, throughout this part, if you have questions, just raise your hand, and one of the helpers will come in and help you. Okay. So go ahead, in MATLAB, hopefully you have MATLAB open. Go ahead, navigate to this directory, and open the file kneereflex.m. It just has a bunch of comments basically landmarks for where you're going to enter code. So the steps for this example are we're going to add models, bodies and joints to our model. Then we're going to add a muscle. Then we're going to add an open loop controller to control that muscle. Then we'll add a feedback controller to model knee-jerk reflex. And then we're going to plot the behavior of that muscle. There are 11 parts to this first section of the tutorial, and we'll be jumping around the file as we proceed. So for each part, you'll fill code into the locations in the file in the appropriate location. So for part A, there's code at the top of the file and towards the bottom. So just make sure to look at the part I'm showing you on the slides. So you can go ahead and now you can fill in this code for part 1. So in this code, we're making the OpenSim methods available in Python and Matlab. Then we're constructing a new model object. We're setting the name of the object, and we're indicating that we want to use the visualizer. So model.setUseVisualizer true. That means when we do a simulation, you'll get a visualizer window. Then towards the end of the file in part 1b, you're going to call a function on the model init system, which returns a state object of the model and finalizes the model. Then in the last part, there's a function OSIMSimulate, in which you provide a model and the initial state for which you want to simulate, and then a duration for simulation. And that will perform a forward integration. And also, that will open a visualizer window. Make sure that you put the OSIMSimulate command at the bottom of your file in the section that has a comment 1C. Again, what that does is it takes a model and an initial state for that model and a duration for simulation, and then it performs a forward integration. Yeah. Okay. Okay. Keep in mind that the comments, the parts are out of order. We're going to be jumping around this file, so make sure for part 1 you put your code in the sections labeled part 1A, 1B, 1C, but those are not all at the top of the file. And if you have any issues, just raise your hand. Somebody will come over. If you haven't got an OpenSim working on your computer, I encourage you just to work with someone else so you don't spend the workshop, fiddling with the software.
simulate function, and the other things were running.
He's using the wrong version of OpenSim. He's not using the download for the workshop. Yeah. You can just close it on Mac. Command C, Command Q. Yeah. Yeah, that's fine. So if you want to close the visualizer window, you can do Control C in the Matlab command window. On Windows, you can just hit the X in the corner of the window. On a Mac, you can do Command Q. If it's
I think it was May 18.
May 18. Okay, that might be. I think there's a more recent version. Well, the other issue might be he might not have he might have to start Matlab as administrator when he runs a configure OpenSim script. Yeah, but he should just work with somebody. Yeah. It means the Matlab we weren't able to edit his Matlab path. He can maybe run. With OpenSim, please just work with somebody next to you. We don't want to spend time getting OpenSim working in Matlab. So please, we really encourage you just work with someone next to you if you're having, if you're still having issues getting OpenSim set up. Okay. So the two most important variables in OpenSim are the model and the state. So I want to talk a little bit more about these variables. So what's an OpenSim model? An OpenSim model is a bag of components. The most common types of components are shown here. So we have a model contains rigid bodies and joints that connect them. A model can also contain constraints, like welding a body to another body or coupling multiple degrees of freedom. A model can contain passive and active force elements. To determine the control signal for an active force element, you can add controllers to your model, such as a reflex controller that we mentioned earlier. And you can also define your own custom components. So you can add your own custom joints, like the ellipsoid joint. You can add custom constraints, custom forces. Every component, you can have a custom version. You can add a metabolics model, for example. So OpenSim turns that bag of components into a set of equations that define your system. So you can also think of a model as your equations of motion and the constant parameters of your system. The complementary object in OpenSim is a state, and the state contains the values of the variables in these equations and contains everything that's time varying. So there are two types of methods in OpenSim that you might encounter, ones that take a state argument, like calc mass center position, and ones that don't. So in this case, get gravity is returning a property of your system. It doesn't depend on your state, that's constant. In this case, that's the acceleration due to gravity. But methods that take a state like this, in this case, we're returning this position of the center of mass of the system, which is a function of the generalized coordinates, and so that's a function of the state. So that separation of model and state in OpenSim is a key concept of our API, and that separation makes OpenSim flexible and reduces errors. So where do states come from? The model can provide you with the default state using init system, which you saw earlier. You obtain states from forward simulations. You can obtain states doing inverse kinematics, where you're fitting marker data to obtain joint angles. And you can obtain states through trajectory optimization methods. OK, so most of you have probably now run this part, this first part, and you should see a visualizer window that doesn't have anything in it, just a ground. That's because we haven't added any bodies yet. So you can close this window by hitting escape once to end the simulation, and then you can hit escape twice a second time to close the visualizer. At any time, if you want to close the visualizer or stop running the currently running script, you can do Control-C in the Matlab command window. OK, so the second part here is to add our first body to the model. So we're going to add a body for the thigh segment. So before we do that, we'll specify some constants we'll be using. So we can provide what will be the hip height of our model, the link length for both the thigh, and also later we're going to add a shank body. So we'll use that link length and also a link mass. So you can go ahead and define those. Then to create a body, we use the body class constructor, and that takes 4 arguments. That takes a string name for the body, the mass, the center of mass, in this case, which is just at the origin of the body, and an inertia tensor. And then we assign that to a variable thigh. So go ahead and do that. Oh, OK.
Are all these units SI?
Yes, OpenSim uses SI units. Yeah. So on its own, bodies don't have any geometry. If we want to visualize a body, we must add geometry to it. You can add all sorts of geometry, boxes, cylinders, ellipsoids, or arbitrary meshes. We usually use arbitrary meshes for the bones you see in an OpenSim model. In this case, we'll add an ellipsoid. And the constructor for ellipsoid takes 3 arguments, the half lengths for the x, y, and z axes of the ellipsoid. So you construct that ellipsoid, and then you call a method on the thigh body called attach geometry, and you pass in that ellipsoid. And then once you've attached geometry to the thigh body, you can add that thigh body to the model using a command model add body thigh. No, it's separate. Yeah, you'll see that later. So now that you've added the thigh body to the model, if you run the script again, you should see the ellipsoid, and if you hit enter, the ellipsoid will just fall. So the reason the thigh body just falls is that if you add a body to a model and you don't specify a joint, OpenSim will connect that body to ground using a free joint. That's fine. Yeah.
If you run block by block, sometimes I think Matlab kind of forgets that you set the API, like the
Yeah, oh, okay.
So I don't know how exactly that works.
Okay. Antoine just told me some people are running parts of the script block by block. I know in Matlab you can select a portion of code to run and just run that portion. But in this case, just run the entire script every time you run the script. Don't run the script block by block. The reason for that is that when you run block by block, Matlab doesn't know that you want to have the import line to import the OpenSim libraries that you have at the top of the script. So just make sure you run the entire script every time. So the motion you should see in the visualizer is what I'm showing in this video. You could try running configure OpenSim again, because that's such a Matlab path. Maybe it wasn't saved between restarting across to restarting Matlab.
Yeah. Which, that one?
Sim 32.
It's that OSIM simulation.
Did you start Matlab as administrator? How come you're in that folder? Sorry? Did you start Matlab as administrator? How come you're in this folder?
Yeah, I ran it as an administrator. They told me to do it.
Okay. But you didn't have to do that in general.
Yeah. No, I didn't. Yeah, I like freedoms.
Okay. Would you be okay working with somebody? Because we really want to make sure we can continue the workshop. Is that okay? So in part 2, if you simulate, you should have just the thigh body falling in free fall. But we don't want a free joint. We want a pin joint in this case to represent the hip. So that's what we'll add in part 3. So I'll explain a little bit how you specify joints in OpenSim. Joints in OpenSim are very flexible, as I've kind of alluded to earlier, and that flexibility is necessary to model biological joints. So in an OpenSim joint, you have a parent body and a child body, and there's 4 different frames to think about. For the joint, there's 2 joint frames, one on each body. So the parent body has its body frame and it also has its joint frame, and the child body has a joint frame and a body frame. And a joint describes how 2 joint frames move with respect to one another. So a pin joint says that the child joint frame in red here can rotate about the mutual z-axis of the 2 joint frames, the parent and child joint frames. So to describe how the bodies move with respect to one another, we also have to specify where the joint frames are located within the body frame, and that's a constant in time transform. So to specify a joint, we have to give a parent body for the joint, the location in the parent body of the joint frame expressed in the parent body frame, and also a child body and the location and orientation of the child body joint frame expressed in the child body frame. So in our specific model, we have what looks like this, where we have a ground body, which will be the parent body for our pin joint, which is shown by these red and blue frames here. And we have a thigh child body. So the location of the joint for the parent body, so the parent joint frame here is here in blue, and the location of that frame expressed in the ground body frame is a distance hip height in the y direction in the ground frame. And then, so that tells us where the parent joint frame is. And then the child frame for the joint, we specify as being a distance length over 2 in the y direction expressed in the thigh body frame. So in code, this looks like the following, where you can construct a pin joint object. The first argument is the name for the joint, so hip as a string. And then we specify the parent body, then the location of the parent joint frame, so this blue frame expressed in this gray frame here. And so that's a distance hip height in the y direction expressed in the parent body frame. Then for orientation in child, we just leave that as 0. Then we have a thigh child body, and then a location of the joint in the child body, and then an orientation of the joint in the child body, which we'll leave as 0. And then once you construct the joint, you can add it to your model. Once you've added the joint to your model, you should just see the thigh body hanging in space, and that's because its default pose is an equilibrium pose. For a pin joint, a pin joint in OpenSim means rotation about the mutual z-axis for the 2 joint frames. So if you want rotation about a y-axis, you have to use the orientation in parent and child frames to transform that joint, the z-axis of the joint frames, to be in the direction you want. Is that? Radians. Yeah, right. Okay, so if you run your script now, you should see the thigh body just hanging there at rest. But we want a more interesting initial condition. So we're going to edit the coordinate for the hip joint so that its default value for the coordinate is such that we'll get a swing of the like a pendular swing. So we're going to set the default value for the hip coordinate to be 90 degrees. So each joint in OpenSim can have multiple degrees of freedom, and we call degrees of freedom coordinates in OpenSim. So a pin joint has one coordinate, 1 degree of freedom, but a planar joint has 3 coordinates. A ball joint has 3 coordinates. And so a coordinate object in OpenSim is what holds the default value for a degree of freedom. The coordinate object also allows you to lock a degree of freedom or to prescribe the value of the coordinate through time based on experimental data. So in this case, we want to set the default value of the coordinate to 90 degrees. So you can do that by accessing the coordinate from the hip joint, and then on that coordinate, call the function setDefaultValue and provide 90 degrees in radians. And if you do that and you run your script again, you should get something that looks like this video here, where the thigh body just swings like a pendulum. Yeah, so one of the properties of an OpenSim model is the acceleration due to gravity, and by default that is negative 9.81 in the y direction. Well, it's to more precision than that, but you can set that to 0. For example, for the exercise device shown for NASA, they might want to tweak that. All right. So the next part is to add the next segment and joint to our model. So we're going to be adding a shank body and a knee joint, which are described in this diagram. And now you'll be doing this part on your own. I won't be showing you the code on the screen until I give you some time to write this on your own. As you go forward, something to note is that if you want information about the methods or functions available on an object or class in OpenSim, in Matlab you can use this method called methods view, and you can provide an OpenSim class or object. So if you do methods view of model, you'll get this little window, and it lists all the methods that a model has and the arguments that it takes. So for example, you can see that you can add a body or a marker or a controller to a model. Yeah. This comment here has instructions for the properties that you should give your shank body. So you're going to create a shank body with the same mass properties as the thigh. So you have a linked mass variable that you created before. And you're going to use the same ellipsoid geometry again. You're going to repeat that line. And then you'll add the shank body to your model. And I'll let you do this on your own. I won't show the code yet. Okay. So Nick said some people were wondering about Vec3 and yeah. So Nick said some people were wondering about here we have Vec3 where we pass in only one argument. This ends up creating a Vec3 where each element is 0. And also for inertia, we saw you did inertia of 1. That creates an inertia tensor where the diagonal elements, the principal axes, are all 1 in SI units. Right, and you have to use OpenSim Vec3s or vectors in those cases. You cannot yet use just MATLAB arrays. People aren't doing this installation stuff. Okay. It's a little rough. turn the mic off. I can put this in off or standard. Either one.
You want to turn it off for a second?
So here's what you should have for the Shank body. Again, here we add a Shank body. I named it Shank, and for the constructor, the first argument is the name. Shank is what I used, and then you provide the mass, the center of mass, which again this expands to 0 for each component, and then inertia that puts the principal axes at 1. Then we use the same ellipsoid geometry, construct it again, and then we add the Shank to the model. So the next part is going to be adding, I'm going to give you some time to add a knee joint to your model. And so here are the instructions. You can also refer to this diagram. You want the parent body to be the thigh and the child body to be the shank. And you want the location of the joint in the parent body to be negative length over 2 in the y direction. Again, that's expressed in the thigh body, so in this gray reference frame. And then the location of this joint expressed in the child body will be plus length over 2 in the y direction. So go ahead and do that on your own. If you're trying to understand how the joint definitions work, you can play around with these arguments. You can try changing the location in parent or location in child to get a sense of how the joint definitions work. Okay, so now that if you've gone ahead and done these steps and you run the script, you should get a video that looks like this. So now we basically have a double pendulum. Okay, so so far our system has been passive. Now in part 6 we're going to add an actuator. So OpenSim has a wide variety of actuators, the most common of which is a muscle. We have a few different muscle models. We're going to use one called Matlab 2012 equilibrium muscle. So you can construct the muscle using the constructor for that OpenSim component, and you can assign that to a variable that I've called vastus. Then you can set the name for that component, that muscle. And then we set 3 of the properties of the muscle. So the max isometric force is the force the muscle generates when it's at its isometric, so it doesn't have any shortening velocity or it's not lengthening, and also when it's at its optimal fiber length. So at this point here, and at this point here. We also set the optimal fiber length, which basically scales the x-axis of this force length characteristic. And we also set the tendon slack length, which is the length at which the tendon goes slack. That's a parameter describing the length of the tendon. So some muscles have really long tendons and long compliant tendons, while others have short tendons. And so with properties like this, we can scale our generic OpenSim muscle model to describe any muscle in our body. If any of you are still in the previous part 5, make sure you add the knee joint before running your script. Okay, so we've set some properties of the muscle. Next we have to define the location of the muscle path in space. And to do this, we specify we're going to add 2 points, an origin for the muscle path and an insertion. So the origin is going to be a location on the thigh body, right here, and the insertion will be a point on the shank body. And so the vastus, the muscle has a function, add new path point, and you specify a name for the point, the body the point is on, so here thigh, and then the location of the point in that body. So the location of this origin point, here we're specifying as length over 10 in the x direction expressed in the thigh body, and then 0 for the y and z components. Then we add an insertion point on the shank, which is this location here, at the coordinates described by this insertion vec3. Once you define those path points, you can add the vastus muscle to your model using add force. And that's in part 6a. And then farther down in your script towards the bottom, there's part 6b. Make sure you fill that part in, and make sure you fill it in the right location. And this line is altering the state that you have, so that the fiber length state is such that the fiber and tendon in the muscle is that the force in both components is the same. So it's putting the muscle in equilibrium between the fiber and tendon. And once you do that, if you simulate, you should see something like what's shown in the video here. So you can see a muscle path in your simulation now. Remember that part 6b is towards the end of the file. So does anybody notice anything weird about this video or something not quite physiological? Yeah, so the muscle path for the vastus goes right through the knee joint, which I'm not able to do myself. So the issue there is we can fix that by adding wrapping what we call muscle wrapping. So you can add geometry to your model that constrains the path of the muscle. So here we add a cylinder at the knee joint, where we're calling that the wrapping surface of patella, and the muscle path will wrap around that patella to prevent the muscle path from going through the knee joint. So to do this, you can construct a wrapped cylinder object. You set its name to patella in this case. You set the location of the patella of this wrapped cylinder, expressed in the thigh body. So that's the location will be negative length over 2 in the y direction, expressed in the thigh body. You also set the radius and length of that cylinder, and the quadrant specifies the direction that we want the muscle to wrap on, the side of the cylinder. So once you create the wrap cylinder, you can add that to the thigh body. And then once you've added the wrap cylinder to the thigh body, you can tell the muscle to wrap around that wrap geometry with this line. Vastus, get the geometry path for the muscle. So each muscle has a geometry path that describes the path it takes, and that's used to compute the moment arm for that path, and also the length of the path. And so you can add the patella as what we call a path wrap to the geometry path. And once you do that, you should have something that looks like this video, where now the muscle path at least initially, does not go through the knee joint. There's some other issues that you can't bring your shank all the way around. And that's something that you can fix by adding passive elements to your model, like ligaments. And that's something we won't add to this model, but you'll see that later on. If you're falling behind and you want to catch up, there's a file in the same directory called new reflex answers, which has the answer code to each of these sections. You can refer to that if you want to catch up. Oh. Yeah, that's specifying the location, the center of this wrap cylinder expressed in the thigh body frame. That's because we add the patella to the thigh, and so the translation is interpreted relative to the body you add the wrap surface to. Set quadrant says the direction, the side of the cylinder to wrap on. So positive X means the muscle should wrap on the positive side. If you did negative X, it would wrap on the other side. Okay. So our goal is to simulate a knee-jerk reflex. So to prepare for that, we're going to pose the model in a sitting posture. So we're going to lock the hip coordinate and set the default value for the knee coordinate, so that the model will be in this pose initially. So to do that, go to part 8A. Make sure you go to the correct portion in the file, and for the hip, get the coordinate for the hip, and then set default locked to true. And then farther down, or in part 8B, for the knee joint, get the knee coordinate, set the default value for that coordinate to negative half pi, so negative 90 degrees. And then you should, if you simulate, you should see the same thing as in this video. So one thing you'll note in this video is that the shank moves a little bit, and that's because the muscle can generate passive forces. And so that means in the default pose, the muscle is actually stretched a little bit beyond rest. Okay. So now we added an actuator, but we didn't specify its control signal, so the system is still passive. Now we're going to specify a control signal for the muscle, so that's kind of like modeling the nervous system. So we can use OpenSim controllers to do this. OpenSim has a bunch of controllers, the most simple of which is a prescribed controller, which is just an open loop control signal as a function of time. So you can, you can create a prescribed controller. I've named it brain here, and then you can add the muscle to the brain controller, and then the controller has a function, prescribed control for actuator, which has 2 arguments. The name of the actuator, so in this case vastus, and then a function of time, which is shown here. So we have a step function, and the arguments here, the first 2 indicate the time over which you want to transition from 2 different control signal values. So between 0.3 and 0.35 seconds, we want to transition from a control signal of 0.05 to 0.5. So this graph shows a control signal as a function of time. Once you've prescribed a control signal for the vastus actuator, you can add that actuator. You can add that controller to your model with add controller. Once you've done that, if you simulate, you should see what's in this plot. The knee extends now, and you can see the activation level of the muscle as the color of the muscle path. So initially the muscle path is blue. At 0.3 seconds, it starts lighting up and becomes red. We have a question about why the muscle swings back even if the muscle still has the same activation, same control signal throughout. And the muscle, so this control signal doesn't specify the force in the muscle, it specifies an activation signal. And the muscle force depends on its length and velocity. So as the muscle, as the knee extends, the length of the muscle fiber shortens. So even though it has the same activation, it has a smaller force. In this case, we use the step function as a control signal, but OpenSim allows you to specify pretty much arbitrary functions. So there's a sine function, but there's also splines where you can specify all the spline points, spline not points, or piecewise linear, piecewise constant. There's a library of functions. You have to build the OpenSim function spline from your Matlab array. Yeah. Okay, so we showed you one controller that was an open loop controller, but now to simulate the knee-jerk reflex, we're going to use a closed loop controller, a feedback controller. So we're going to disable the open loop controller, and you can do that with brain set enabled false. Then we're going to add a reflex controller called toy reflex controller. So you can construct that component, assign it to a variable. Here I've named it reflex. Then you can add the vastus muscle to that controller. The way this controller works is basically it excites the muscle. It's a negative feedback, so it's just a gain times the lengthening rate of the muscle in a negative sense. So we set a gain for the reflex, and we add that controller to the model. Then farther down in your file, at the part labeled 10b, we're going to model the perturbation to the Shank. We're going to set the initial speed value for the Shank degree of freedom, the knee degree of freedom, to -3 radians per second. So at part 10b, you can get the knee joint, get its coordinate, and call set speed value on that coordinate, and you provide the initial state of the model and the value you want for the speed of that coordinate in your state. Now, once you've done that, if you simulate, you should get the following. So I'll play that again. Initially, the knee flexes because we've set an initial speed, but very quickly you see the muscle lights up and turns red, and that's the reflex controller kicking in. Literally kicking in. Okay. Okay, so now we've been able to simulate a knee-jerk reflex, but we want to understand this motion a little bit more, understand what's happening with the muscle behavior. So to do that, we're going to plot some quantities from our simulation in Matlab. So part 11, we're going to add a reporter to our model, and a reporter lets us extract quantities of interest from our simulation. Most OpenSim components have what we call outputs, so quantities that you can get out from your simulation. And so for example, the muscle has outputs for its force, its length, its power, and stuff like that. So for the reporter, we're going to create a table reporter, which basically stores a table of your simulation the desired simulation quantities inside internally, and then we set how often we want to get our report. So we're going to say every 10 milliseconds we want to evaluate our quantities of interest, and to specify those, the reporter has a function add to report, and this function takes two arguments. It takes the output, an output from an OpenSim component. So in this case, we get the normalized fiber length, so the length of the fiber normalized by the optimal fiber length. And so you can do muscle get output normalized fiber length as a string. And then the second argument to add to report is a column label in the table for this output. So we want two outputs. We want the normalized fiber length, and we also want the active force length multiplier. And we abbreviate that using the column label FL. And once you've specified those two outputs, added those two outputs to our reporter, you can add the reporter to the model. Then in part 11b, farther down the script, we are going, after the simulation, we want to extract that table, extract these two quantities. we have a function, an OSIM table to struct, which converts an OpenSim data table to a Matlab structure. We'll display the field names in that struct. The field names in that struct are basically the time and then the columns you specified earlier. So that struct will have fields LM and FL, and we're going to plot those two. So we're going to see a snippet of the force length curve, the portion of the force length curve that this muscle goes through during the knee reflex simulation. So now if you've run this part, you should see a MATLAB. So after you simulate, you'll run a simulation. Then if you hit escape twice, or if you hit escape once, you'll get this Matlab plot window. And this plot, again, is showing the active force length multiplier as a function of the normalized fiber length during your simulation. And so this shows the portion of the force length curve, which is this curve here that I showed earlier. So this is a portion of the force length curve that the muscle goes through during the knee reflex motion. And you can see that the muscle during this motion is operating pretty much at optimal fiber length, which means it can generate a lot of force. So we might be interested in understanding how this muscle behavior changes if we change the properties of the muscle. So we're going to make a pretty drastic change to the vastus muscle. We're going to change its optimal fiber length to 0.39 meters. So go ahead, find, in part 11, change this. So find the line where you change the optimal fiber, you set the optimal fiber length of the muscle, set it to 0.39, and then rerun the simulation. And maybe before you do that, maybe think about what you think will happen to where the muscle operates on the force length curve. Where do you think we'll see the muscle operate now? Okay, so if you rerun the simulation and you exit the visualizer, you'll get this updated plot. I should have said don't close the plot window, because then this new plot will be added to your existing plot. And what you should see is the following. This red curve shows where the muscle operated on the force length curve now with your updated optimal fiber length. And you can see that with the greater optimal fiber length, the muscle ended up operating way farther down what we call the ascending limb of the force length curve. And that means the muscle couldn't generate as much force. And so in your video, I don't have it here, but locally you should have seen in your video, the muscle swings, it flexes a lot more. That's because the reflex, even though it's generating the same activation, the muscle is at a much shorter normalized fiber length, so it can't generate as much force to counteract the perturbation. Okay, so this is part 11. This is the last part of the hands-on workshop. We're going to wrap this part up now. So this type of analysis I showed you is similar to the one from Greg Sawicki and Dom Ferris, where they analyzed the force length behavior of the plantar flexor muscles. And so you can perform this type of analysis pretty easily now and study how different motions and different muscle properties affect muscle behavior and your motions. So in this portion of the workshop, you learned how to create an OpenSim model from scratch. You learned some of the most important OpenSim components. And you learned how to extract quantities from your simulation and plot them directly in Matlab. As you go forward, there's tons of resources to guide you. Our wiki, what we call Confluence, has lots of examples for beginners using the standard OpenSim workflow and tools, scaling, inverse kinematics, inverse dynamics, through complex advanced tasks like building a custom muscle or a custom controller or performing an optimization, like a trajectory optimization. If you want detailed methods, detailed information about what methods the API has, the different components in OpenSim, we have a website we call Doxygen. That's documentation for our API, our application programming interface. That's basically like, if you want more information than methods view can give you, you can use Doxygen. We have on our support website what we call OmniSearch, like a search bar that lets you search across all of our support websites, all our documentation in one place. And then OpenSim is open source, so all of our source code is online on GitHub. And GitHub has some great search features too. You can search for examples in the code base directly. So we'll take a 5-minute break here. And during the break, you can also ask any questions. Well, before we take a break, does anybody have any questions they want to ask? Okay, so let's take a 5-minute break. We'll come back at 10:32.